Another application of integration is finding the average value of a function. So let's think about some things we've done in the past with velocity. How can we find average velocity? Well, the average velocity would be, I'm going to use P for position, the position at, let's say, the end value minus the position at the beginning divided by the change in time. So the change in position over the change in time. Average. How would you find average acceleration? Well, change in velocity over the change in time. Well, let's think about how we could use integration to help us find this. Well, let's look at this formula. 1 over b minus a times the integral from a to b of at. Well, this would be, let me rewrite that as 1 over b minus a times the antiderivative of acceleration is velocity, so velocity at b minus velocity at a, which is the same as velocity of b minus velocity of a over b minus a. What about this expression? Well, again, we have 1 over b minus a. The antiderivative of velocity would be position. So the position at b minus the position at a, which is equivalent to p of b minus p of a over b minus a. So the average value of any function can be defined as 1 over the change in the x values times the integral from a to b of that function with respect to x. Because remember, this is actually average acceleration, and this is average velocity. So if we were asked to find the average value of this function from 1 to 3, we would take 1 over 3 minus 1, the change in our x's, times the integral from 1 to 3 of x cubed times the square root of sine squared x, which in a calculator we'd have to do sine of x squared dx. And that is a calculator-based problem, so let me grab my calculator. So that's going to be 1 over 2. Make sure we see how to put it in. 1 over 2 times the integral of from 1 to 3 x cubed times the square root of sine x squared. Arrow over, whoops, not d4, what was I doing? dx. And I get 0.422. Now this one says non-calculator. Let's see if we can do it by ourselves. So the change in x is 6 minus 2. We're finding the average, so we're taking the value accumulated from 2 to 6 of 2 minus 4x dx. Oh, at least they gave us a nice one. So that's 1 over 4. Let's see, the antiderivative derivative would be 2x minus 4x squared divided by 2, evaluated from 2 to 6. So 1/4, I'm going to plug in 6, so 12 minus 2 times 6 squared minus, evaluated at 2. That's 2 times 2 squared, that's 8. So 12 minus 72 is going to be a negative 60. 4 minus 8 is going to be a negative 4. So 1/4 of negative 60 plus 4 is going to be negative 56. And 1/4 of that is negative 14. A ski resort uses a snow machine to control the snow level on a ski slope. Ignore that, I don't know what happened there. Over a 24-hour period, the volume of snow added to the slope per hour is modeled by the equation S of t equals blah, blah, blah. So this is the snow added. The rate at which the snow melts, let's use a different color for that. The snow is melting by m of t. Both S of t and m of t have units of cubic yards per hour, and t is measured in hours from 0 to 24. At time 0, important information, the slope holds 50 cubic yards of snow. Okay, so let's think. Compute the total volume of snow added to the mountain over the first 6 hours. Total volume of snow added. So how much has the snow changed in the first 6 hours? So that would be the integral from 0 to 6 of the snow that's being added. Well, the rate that it's being added is this function. So of 24 minus t sine squared t over 14 with respect to time. Now, I'll give you a hint. When you're doing problems like this, and this is definitely a calculator problem, I like to take my functions and store them. So I'm going to call this one y1 and this one y2. That way I don't have to retype them every time. So y1 is going to be 24 minus, and we'll use x, times sine of x divided by 14 squared. And y2 is going to be my other function, 10 plus 8 cosine of x divided by 3. Make sure I'm in radians. Oh, I'm not. Change it back to radians. Okay, so this is y1. So what you can do is when you go in to do the integral, you're going to go from 0 to 6. But instead of retyping that equation, since I stored it into y1, I can go alpha, trace, and look at that. Those are all my y variables. I'm going to say y1 dx. So I get 142.413. And that was cubic yards of snow. Find the value of the integral from 0 to 6 of m of t. So, integral from 0 to 6. Now, stored m of t in y2. So, alpha trace down to y2 dx. Gives me 81.823. What does that mean? What does it mean? Well, that's the snow, the amount of snow melted, over the first 6 hours. Or you could say from t equals 0 to t equals 6 hours. What does the next one mean? Well, first let's find it. 1/6, 0 to 6, m of t dt would mean I take that value that we just found divided by 6, and it's 13.637. What does that mean in the situation? Well, that is the average amount of snow amount of snow in cubic yards, amount of snow in cubic yards, melted, I keep forgetting to write melted, in cubic yards per hour. Is the volume of the snow increasing or decreasing at t equals 4? So we need to figure out the whole volume of snow, or the amount of snow that's fallen. So let's see. The amount of snow. Well, we started with 50 cubic yards. We're adding the snow that's being added, and we're taking away the snow that's melting. Now, to figure out if we're increasing or decreasing, we need to figure out the rate that the volume of snow is changing. So that would be the derivative of that total volume, which, oh gosh, that looks like it's going to be really complicated, right? Well, that's the derivative of 50 is nothing. The derivative of an integral, you're going to get that rate back minus the rate that we're melting back. And we want to find out if we're increasing or decreasing at time 4. So we need to find the total amount of snow at time 4. Whoops, the DTs are gone. Oh, goodness, I'm not awake. So, since I stored those values in my calculator, I can pull up y1, evaluate at 4, minus y2, evaluate at 4. I get 11.800. So what does that tell us? Well, since A prime at 4 is positive, the volume of snow is increasing at t equals 4. How much snow is on the slope after 5 hours? Well, that'd be easy. That's going to be the total amount of snow at time equals 5. So 50 plus the amount of snow added minus the amount of snow melted. Good thing we saved those. 50 plus the integral from 0 to 5 of the snow being added, which was our y1, minus the integral from 0 to 5 of the snow melting, and we get 95.335 cubic yards. Suppose the snow machine is turned off at time equals 10. Write, but do not solve an equation that could be solved to find the time k when the snow would all be melted. So we need to figure out how much snow we have at time 10. Well, that would be easy. That would be 50 plus the integral from 0 to 10 s of t dt minus the integral from 0 to 10 m of t dt. And if we took the amount of snow at time 10 and subtracted how much is accumulated from 10 to whatever time, m of t dt, where there was no more snow left. And we could actually calculate that value pretty easily to find out how much snow is at time 10. Well, I could just go in and edit that last expression. And at time 10, we have 183.193. 83.193 cubic yards of snow at that moment. So 183.193 minus how much melts from time 10 to some time k. We want to know when that equals 0, when we're out of snow. Now notice it said write but do not solve. You'll see a lot of those on the upcoming AP test. All right, the next one. Let f be the function defined by this piecewise function. We haven't done a lot with piecewise functions, so this is going to be interesting. We want to find the average value from 0 to 5. So let's just set it up first. That'd be 1 over 5 minus 0 of the integral from 0 to 5 of f of x dx. Well, f of x is split up into two parts. So we would have to separate this out into two parts as well. We'd have the integral from 0 to 3 of the square root of x plus 1 dx plus the integral from 3 to 5 of 5 minus x dx. And we can find that using our calculator, just plugging it in. But just to review some of our skills, how would we do this by hand? Well, since the derivative of the inside would be 1, we don't have to use u substitution there. It would just be x plus 1 to the 1/2 add 1, that'd be 3/2 times 2/3, evaluated from 0 to 3. And then we'd have 1/5 of the antiderivative there is 5x minus x squared divided by 2. And that part is going to be evaluated from 3 to 5. So 1/5 of 2/3 of 3 plus 1 is 4 to the 3/2 minus 2/3 of 0 plus 1, which is 1 to the 3/2, plus 1/5. If we plug in 5, we get, let's see, 5 times 5 is 25 minus 25 over 2 minus, when we plug in 3, we get 15 minus 9 halves, and so forth. Square root of 4 is 2. 2 cubed is 8. That would be 16 thirds. Minus, that's 1 2/3. Plus 1/5. Let's see, let's kind of break it up. We've got 25 minus 15 is 10. That'd be a negative 25 halves plus 9 halves. Negative 25 plus 9 would be negative 16 halves. That's an 8. So 10 minus 8 is 2, so that'd be 2/5 here. 16 minus 2 is 14, so 14 thirds. That'd be 14 over 15. Change that to 6 over 15, and we get 20 over 15. The next two problems I want y'all to try on your own, and then we will go over them in class.